What's up, guys? Crisco here, Crisco Designs. We looking into getting a new 3D printer at work, thanks to moi. So I been reaching out, and I used the Markforged before, so I kind of recommended it for what they do at our GM plant. Because we have a test lab, development lab, so they could use that kind of technology. Markforged is inlaid carbon fiber prints with like a nylon, plain nylon, or a nylon with carbon fiber strands. It's their onyx material, and they're the only ones that I know of that are doing like the strands. So you can make something out of plastic, but it can be super strong, like, you know, steel or aluminum, and very durable. So we went up there, they had an open house. Basically just gonna play some of the footage from that open house, they talked about the printers, give us some information, and find out what we needed it for. So, alright, hope you guys enjoy. Their printer's pretty cool. Like, it's not very mainstream yet, but it's pretty cool. It's out of the price range for, you know, the average Joe, me and you. Starts out like maybe $4 grand for like the base model. You can get all the way up to their model that has like a laser vision system built into it, and that's like 80 grand. Then you got their metal printer, which hasn't come out yet. That's like, by the time you add all the accessories, it's about 200,000. So, all right, hope you guys enjoy. Comment with any questions. I know a little bit about the printer. I've used it, so I can help answer your questions, and maybe you want to see some more detailed parts. I got some, so all right.
Usually kind of where Markforged got to start and creating really strong parts.
Is this the same infill with your continuous fibers? You've got, I see you've got a lot.
Yeah, so
And hollow.
Kind of explain the differences. We have two like base materials. We have the nylon, and this is more of like a nylon 6 blend. It's our proprietary.
One of these, but nylon or
we bring this part around because this is like, if you were just to fly through our software and just say, did it at all standardized settings, just hit print, this is the type of part you're going to get with the nylon. We have our other base material, which is our onyx material, and so this is now incorporating carbon fiber powder into the nylon 6 material. And part of the reason is you get overall improved stiffness, just overall tensile, strength from it.
And that's straight up the way it comes.
Yes, and so this is the part of the reason why I bring this part as well, is that you get the comparison between the nylon, base nylon, and this, and so you can kind of feel the stiffness and the rigidity that you get. This is done with the same parameter settings as that nylon.
Well, that's what I was asking. This is the same.
So this piece here, though, this is incorporating the actual carbon fiber filament in there.
Okay, so two-process.
It's a dual extrusion head on it. Yeah, so like you have actually on your head here, you have your fiber that comes into, or your actual filament that comes into this head here, and then you actually have your fiber that comes into this here. So you have your carbon fiber spool here.
Got it.
And that's kind of the key differentiator. We're the only company in the world that incorporates true fiber into our parts, and so like, when you start talking about it, you can, significantly, feel the difference.
So I guess my question, I'm trying to get a grip on. I understand the fibers in here definitely would strengthen it up, but so I can definitely see your infill as being much smaller. Are you using the same infill in this?
So it's a little bit different in the sense that when we bring these to a lot of shows, we have people trying to break them all the time. So this part here is jam-packed with every last bit of carbon fiber that you can
So it's
get.
a solid fill.
So this is a solid fill on it, but with that being said, you have control over how you do fill that in. So realistically, I don't have to jam-pack this thing full of carbon fiber. We do, just because everyone goes ahead and tries to break it. So, more often than not, like, what we use is just sandwich theory, in the sense that, like, when a part's exposed to flexing and having, impact on it, really the biggest advantage you can get is just doing the top and bottom panels.
Like an I-beam.
Yeah, exactly.
Sure. Yeah, I get that. I just was curious because it's a lot stiffer, but it's also, if you made the nylon and it's a solid, it would be much stiffer too.
shape of the part. They're great for impact resistance as well. So typically anything that's going to be on a manufacturing line that's really going to be just taking a beating, that's usually what we kind of look for on that. We have our just base fiberglass, and that's for kind of really taking parts out of, when you look at a lot of desktop printers, that adds a significant amount of strength to it with a really not a significant amount of cost added onto it. So like our Onyx Pro series, you can do all our base Onyx material, but you can incorporate fiberglass into it as well. So, and that's the only fiber that you can use on that machine specifically. But you can get, significant strength improvements that kind of beat out pretty much anything competitor-wise in that realm. And then we also offer our high-strength, high-temp fiberglass. So where that one really comes into play is something that's going to be exposed to some high levels of heat. And we can now get heat deflection temperatures up to about 150 degrees C. So something that might even be actually put into an oven, and we have some customers that are doing like thermoset molds that they were typically doing out of silicone before, and now they're printing out of our Onyx incorporated with the high strength, high temp fiberglass, and they can throw it in the oven for a few hours at 250 degrees Fahrenheit, and it's just fine. And then the step up from that, when you start looking at parts that might be replacing stuff that you've done in aluminum in the past, that's when you start incorporating carbon.
The rocket motor I saw, was that made out of the high temp fiberglass?
The rocket motor.
It was on your guys' website. It was like a case study.
Yes, yeah.
Got it.
So honestly, my favorite material to work with from a price standpoint as well as just the overall performance is the high strength, high temp fiberglass, just because it has great thermal characteristics to it, and overall the actual strength that you get from the part is pretty significant.
Do you have to use your materials, or do you buy other materials? Or is it?
Realistically, so the way we describe, you're essentially avoiding your warranty if you start using materials outside of it. So you don't have the ability to change temperature settings and things like that on it. So if you were to go out, there are carbon fiber filled nylons out there, but we can't guarantee that it's going to work.
Right.
We don't know the specs that they
So
created.
how is your pricing compared to other?
I'm not gonna lie, it's a little bit more, but at the same time, pretty much, at least from what I've seen out in the market, there's two differentiators in the filaments that you're gonna get that are carbon fiber. One, most of them use chopped carbon fiber as opposed to we use powdered carbon fiber, and the reason that is significant is you get a much smoother blend overall in the actual filament, so you get better thermal characteristics, and then more often than not, when you expose the two filaments to tensile testing, the chopped carbon fiber, because it's not very uniform in the actual filament, actually performs worse than the base would in tensile testing, where we perform better in tensile testing using powder. One of the other kind of things to keep an eye out for is we use, again, our base nylon is a nylon 6. It's a proprietary blend of it, but most of the outside filaments that you're going to find are nylon 12, and those nylon 12 is a little less chemical resistant than nylon 6. Those are...
Well, it's like, going to buy a regular printer.
It's a combining two different existing processes. So the actual getting your part printed is exactly the same. So the internals, the guts of the way the machine works is almost identical to what you're looking at here. So it's our FFF, fused fabrication process. And then from there, we take it into like a metal injection molding process. And I'm not sure if you guys are familiar with how that's done.
No.
But essentially what it is you have, it's a green part. So the actual material that we use is two binder plastics mixed in with powdered metal. So then you basically print that out, via the same process that you would. You end up with what's called a green part. You take that to a wash station, and that sits in this bath that washes out one of the two binders in it. And then from there, you kind of have this spongy-like piece. You take that to a sintering oven. That then vaporizes out the last of the binder material, and you're left with your fully dense.
So
Interesting.
So it burns off the other binding material, but it doesn't fuse. So I'm familiar with powdered metal. Compress it, right? So it holds its shape. It does have some find your single speaking of that, but then you essentially heat treat it or autoclave or something high temperature. If you use things together with that point. So
It would still help out with
fusing
that.
the materials together, so you get enough of the high temperature.
There's no.
It's on a melt temperature, it's a different part of that transition.
Yeah, it's like
phase,
that transition phase, right? So we are getting, and where I can kind of touch on probably where you're getting at with it is usually in like a FDM process or FFF process, you get anisotropic performance out of the part. Whereas if you were to pull it in the XY direction, it's going to get different results than if you were to pull it in Z. So when we have our metal parts and the testing that we've done, we get isotropic performance out of it. So you actually are getting to that point where it's starting to melt those metal particles together. And right now we're going to release the actual material data at some point, more or less when we actually start shipping out the machines. But the testing that we've done right now, we're looking at densities of upwards of 99.5%. So, and that's localized density.
So the one that's the metal printer, that's this?
That's the Metal X. So this is the Mark X, then we have the Metal X.
And the metal only does metal.
Yes.
Okay.
Yes. So, and then this, essentially it's
So what would
really
be the
simple
advantage of bumping up to this versus that one? Because that's a big, huge difference, right? This one's like 60 grand or something?
Yeah, this one's 69.
Okay, yeah.
So really the advantage is you have a larger build platform, so some customers really want to utilize that larger build platform. Ultimately, that's where extra cost comes in, needing some, just having the software be able to account for the larger build volume and having the larger build volume and all the mechanics behind it.
But it, to me, it doesn't look that much bigger. It does look wider, but this way it looks similar, right?
It's overall. Are you guys more metric? Or are you more imperial?
inch.
Okay, so it would
me.
be 13 by 13 inches by 10 inches by 8 inches. And then that one is, I believe it's
13 by 5 by 6, right? 12 by 5
I think it's 10 by 5. Yeah. So
We'll give you a USB stick with brochures on it.
Yeah.
And there's all the information. But the other thing that's really nice about this is the laser system on there. So I don't know, how if you guys need to like validate parts, that need to be perfectly accurate. They actually put a laser micrometer on the print head, so you can measure at a specific layer if you want. And leveling the bed is a lot easier too. So not a huge feature with bed leveling. We think it's awesome. It doesn't sound like
doing this
it.
for 2 years. It's easy. I'm like, why would you need that? Now I'd rather have that than the automatic
You usually
bed
get what you pay for.
The auto bed leveling is becoming like a standard feature in printers nowadays.
do half of it with a concentric fill and half of it with an isotropic fill. I could, and from there I can start to tell it like, okay, I need every layer to have fibers oriented 135 degrees, or I need it to alternate from 45 to 90 to 100, so I really have the ability to make it as simple as I want, all the way to as complex internally as I want. And realistically, after using a lot of different softwares out there, there's plenty of software where you can just get lost in the amount of buttons in there, and it takes sometimes like months to be able to master what you're even looking at. This, I highly recommend getting the download that he was talking about. Go through it. It takes more than a few minutes to really learn what you're doing, and the visuals behind it are very impressive. The way it just kind of lets you know what's actually happening. There's a lot of tips and tricks that pop up that you know what you're doing. If you have questions, things like that. So really,
the demo is it all full capability?
all of it.
Just like
You won't have
some
metal.
days or
You won't have metal capability to do costing and stuff like that. If you guys do want some cost and time estimates, they can get you in touch with me, and I can do that. No problem. So realistically, this is the workhorse behind our software. This is when you want to fully utilize what our machine is capable of. This is where you're gonna really be looking.
And the nice thing is, if you do have one of each, it's the same software. When you have build the part, you just tell it what printer you're going to. And then there's different features for the actual system too.
In my mind, I'm still trying to wrap my head around 15,000, 70,000. How?
Laser components aren't cheap.
Yeah.
That's what I'll say. Laser and laser controls.
It's the majority of it.
Yeah.
Lasers are extremely, so like to put it in perspective, that laser in the XY plane is accurate to plus or minus 50 microns. In the Z stage, it's accurate to 1 micron.
So essentially, that printer can print more accurately than the other.
Yeah, so there's two reasons why. One, bed leveling, pretty significant in the sense of the first layer. First layer is by far the most important layer on your entire metal, and that ties into good bed adhesion, getting a level first bed so that you're not essentially building a cockeyed piece, or possibly damaging your tip because it's too low, things like that. So really good for that. The second is in-process inspection. So when you start talking about holding the proper tolerances, that's where that comes into play. So if I'm building a part that might take 2 days to build, and I need to know that internal diameter of some piece needs to be within 20 microns for it to work, and all of a sudden I print my part, it takes 2 days, I get it, and I realize, hey, this isn't the size I need. Well, then I just wasted all that time and material, right? Well, I can have it actually scan that individual layer, like mid-print, basically essentially pause at that point, take a scan of it, you can email with all the data, take a look at it, say, oh, okay, it's good to go, let it finish printing, or no, I need to stop the print and reset. So when you start talking about those extremely tight tolerances, for some aerospace applications and stuff like that, it's pretty